Good morning. So we're going to continue our discussion of magnetic fields and magnetic forces. And today we want to explore what makes magnetic fields and how we can calculate the magnetic fields produced by sources. So to do that, we're going to introduce the Biot-Savart Law, which is sort of a brute force way of calculating how much magnetic field you get from a magnetic source. It works in virtually any situation, but a little bit like when we learned about Coulomb's law, which also worked for calculating electric fields in any situation, it's not always the easiest method to use. And so we'll start today with the Biot-Savart law, this sort of brute force method. Next week, we'll learn about some more elegant methods for certain situations. Okay, so we're going to start by talking about the magnetic field of a moving point charge, and then we'll generalize that to currents, which are going to be more useful because typically we deal with currents in wires. So magnetic fields are produced by moving charges. This is the starting point. We talked about how permanent magnets tended to be in materials where the electrons had some net spin, and the all electrons have spins, but the atoms had a net positive or negative spin. And so more generally, moving charges produce magnetic fields. So if we wanted to calculate the magnetic field at a point over here due to a moving charge passing by over here, what parameters do you think that would depend on? Yeah, Eric? So distance from the field. So if we're over here, the charge is moving over here, the distance between them probably matters. What else? Eric? So the charge itself, whether it's positive or negative, or how much charge there is. Yep, absolutely. We said it was a moving charge, so what else do you think should matter? Vincent? The velocity? Yeah, absolutely. So these are some of the things that should matter. So here's a little diagram showing a moving charge. So there's some velocity vector drawn going left to right. And the magnetic field is drawn at many different points in space. I guess, well, 6 different points in space, to be specific. And what we see is that the points that are closer to the moving charge have a greater magnetic field than points that are further away. So we kind of expect that. And another thing that we see is the magnetic field is sort of circulating around the direction that the charge is moving. So that might not be too surprising either, because we saw magnetic field lines go in circles. So if we thought about like what direction should the field lines point, if we thought about it, it would make sense that they'd have to go in circles, and what would those circle around? Well, maybe the path of the charge would be a logical thing. Other things that may matter is like the angle here between our velocity vector and our position vector of our point relative to our moving charge. That might matter. It might be different if you're at an angle versus if you're at a point sort of perpendicular to that velocity vector. And also the material that you're in, which is characterized by this magnetic permeability mu. This is a little bit like the permittivity of a material epsilon. It tells you about how strong the electric field is in that material. Mu tells us about how strong a magnetic field will be. And this is a different mu than the one we introduced Tuesday. We introduced the dipole moment of a current loop, which was a vector mu. And this is a scalar. So this is just a regular number with some units on it. So you have to be able to tell from context if it's the magnetic permeability or the dipole moment. Okay, so given those quantities that affect the strength of the magnetic field, let's see if we can think about how the expression for the magnetic field might look. Do you think the charge should be like in the numerator or the denominator? Do you think the magnetic field should be proportional to the charge or inversely? Probably proportional. More charge should be produce a bigger field. How about velocity? That should be proportional as well, or at least in the numerator. We'd expect something moving faster to produce a bigger effect. Distance from the charge. Vincent? It would be in the denominator. As we get further away, we expect the effect to be smaller. And it might be smaller by a factor of r, or it might be r squared or r cubed. It's not maybe obvious at this point. This angle and mu, those are a little bit more complex, but here's the expression that we get for the magnetic field of a moving charge. Okay, so we can see it's proportional to mu. This is just a constant of proportionality that tells us how strong the field will be in a particular material. And we also include this factor of 4 pi, sort of in our definition of mu. And we do it for the same reason like when we had the constant of proportionality in Coulomb's law, K. We could describe it as 1 over 4 pi epsilon naught. And the reason we kept that 4 pi separate is because then when we applied Gauss's law, like a lot of geometries cause that to cancel out and simplify our work. So just sort of looking ahead, we will define mu with this factor of 4 pi to simplify things later on. And then we see the charge is in the numerator, the velocity is in the numerator, the sine of the angle is in the numerator. So apparently if we're at an angle along the path of the charge, then sine phi would be 0 and there would be no magnetic field. And then we have this factor of r squared in the denominator. So we expected r to be in the denominator, and we see that it's squared. So this is the magnetic field, or at least the magnitude of the magnetic field, from a moving charge. And for the direction, we're going to use the right-hand rule. So the magnetic field is circling around the wire. And I mentioned last time that one version of the right-hand rule we can use is whenever we have something circling and something going straight, our thumb can point in the direction of the thing that's straight, and our fingers will curl in the direction of the thing that's going around. You can apply that forwards or backwards. You could, if you knew the magnetic field was like this, you could curl your fingers in that direction. It would tell you the moving charges that produced it must be moving up, or in this case, if we know the moving charges are moving up, and we assume that they're positive, then the magnetic field must curl around that in a sense given by this right-hand rule. Okay, so we can draw pictures like this that are sort of quasi-three-dimensional to visualize that, because inherently the magnetic field and the velocity are in different planes. That can be difficult, especially if you're not an artist. So one thing we often do is just if we drew like a top view of this, or maybe let's say a bottom view, the charge would be moving from the bottom view, it would be moving into the page. So here's a bottom view, and then we could draw the lines circulating around it. Again, pointing our thumb into the page, they would curl clockwise. And so we use this X symbol to represent a direction into the page. And that's meant to represent, like, if you shot an arrow into your page, you'd see the X of the tail feathers sticking out. So that means into the page. And then if we have a dot, that represents like the point of an arrow pointing out of the page. So out of the page is going to be represented by a dot, or sometimes we do a dot with a circle around it, since otherwise a dot might just look like a pencil mark or something like that. So we'll use this notation when we're trying to simplify the drawings and not have to draw everything with perspective. Okay, so we've got the magnitude and the direction. And what I'd like you to do is work together with your neighbors to try to categorize these 8 different combinations of moving charges. So, for example, we have some current, which is basically moving charges, here pointing into the page, and here pointing out of the page. And each of those are going to produce some magnetic field. And so if we evaluate the magnetic field at where this dot is, you want to work out the direction of that magnetic field. Is it up, down, left, right, or is it 0? Or maybe it's something in between. So try to categorize these 8 different cards into groups based on the direction of the magnetic field. Use your right-hand rule. Use the notion that the further away you are, the weaker the field will be. Let's discuss this. Let's go through number 1 together and see if we can work this out. So we're trying to find the field up here. I'll use my virtual pointer according to this. We want to find the field up here. Let's first calculate from the wire on the bottom left. How do we find the direction of the field from this wire? Vincent? Okay, point your thumb out of the page. Okay, so our hand has to curl in such a way that our fingers are pointing up and to the left at this point. So our fingers are circulating around counterclockwise. And at this point, that means up and to the left. Okay. And now we'll just add to that the field we get from the other wire. The other wire is going into the page, so point your right thumb into the page, and the way your fingers will circulate around is clockwise. But in this case, clockwise at this point means up and to the right. Okay, so when we add an up and to the left with an up and to the right, we should get an up for the magnetic field. Okay. So I took the liberty, well, there's the solutions. So you can compare this to what you had. Most of these were up. We just went through number 1 together. Number 2 is up because our fingers are pointing up when they curl around at that point. 3 is, why is 3 up? We have 2 different currents. One that points into the page that produces an upward field, and one that's out of the page that produces a downward field. So why don't those cancel? Carrie? Yeah, the one that's into the page, because it's closer to this point, it's going to have a greater magnitude for the same current, and they have the same current. So it's stronger than that one. So its upwards field is greater than the downwards field of this one. So they would produce a slightly weaker upwards field. 4, we have a current coming out of the page, so we curl our fingers, and if I can add my hand onto this so that you can see. So just take a minute to check all of these, make sure they jive with what you were thinking. So the key thing is, you point your thumb, you curl your fingers, and then you look at what direction your fingers are going over at the point, right? So, I mean, at different points, your fingers are going in different directions because of the curling nature of your fist. But we just care about the direction at the point where we're evaluating. Any questions about those? Did anybody disagree with anything I got or have some confusion about any of them? Bella? How do we get 0 here? They're both currents are pointing out of the page. Okay, so why is it that we get 0? So because they're both pointing out of the page, I should orient my thumb pointing out. And that means that for the one on the right, my fingers are curling down at this 9 o'clock position. But for the one on the right, my fingers are pointing up at the 3 o'clock position. No, it's not pointing down because although it's the same current, we're looking at a different position relative to that current. So in one case, we're looking to the left of the wire. In the other case, we're looking to the right of the wire. Because my fingers are circulating around, they're going down on the left and up on the right. Okay, so stare at that for a moment. Maybe you can see that. And if it's helpful, you can always draw, on the paper, a circle going around with little arrowheads all over it and ask what direction are the arrowheads at that point. Okay, so we can quantify this relationship, which before we said we had an expression for the magnitude, and we had a way to find the direction, but we can actually quantify that mathematically with this expression that gives us the magnitude and the direction. So we still got our mu over 4 pi. Before we had qv times sine of an angle. Now we have qv cross r hat, where r hat is the direction from the current to the point where we're considering our magnetic field. And then r is that distance. So we have that distance squared. Okay, so we're not going to really work with this expression directly very much, but we're going to use it to derive an expression for the magnetic field from a current. This is the magnetic field from a moving charge. And of course, a current is just a bunch of moving charges. So imagine you've got a little segment of wire. This is just a segment on a longer wire that forms a circuit with current flowing through it. So we'll say that the current is pointing upwards in this particular case. And the length of the wire, because it's little, we're going to call it dl. So the length is a differential element, a minuscule little element. And that's in the, well, yeah, that's the length. We'll say it has some cross-sectional area A. And we want to calculate the magnetic field up here at some point. And we'll let the vector r be the vector from the center of our little element of current to our point that we want to calculate the field at. So the amount of charge contained in this is just n, the charge density, so the number of charges per unit volume, times the volume of this, which is just the volume of a little cylinder of cross-sectional area A and length dl. And that product, n times this term in parentheses, gives me the total number of charges. And then q is the amount of charge per particle. So if those charges, which I'll call dq, are moving along at some drift velocity, v sub d, in the direction of the wire, and I'm going to call that direction a vector dl. So dl points in the direction of the current and has a length, a minuscule length given by the length of this wire. Then we can use our expression for the magnetic field from a moving charge, where this is the amount of moving charge we have. And we can say the magnetic field I'm going to feel up here from this minuscule amount of charge in this little tiny bit of wire. It's just a little bit of magnetic field, so I'm going to call it dB, some differential element of magnetic field. And then I'm just going to use the expression that I have, mu over 4 pi times the charge times the velocity crossed with r hat divided by r squared. So that's the expression that I had. And I'm doing a couple things here. The velocity, I'm separating into its magnitude, v sub d, the drift velocity, and its direction, which I'm calling dl, the direction of the wire. Okay, so when I do this, I can substitute in for dq. The amount of charge I have is the charge density times the amount of charge per particle times the volume of the little segment. So I plug that in here. And when I rewrite that, I can look at this term in parentheses, the charge density times the charge times the area times the drift velocity. So area times drift velocity, this is meters squared times meters per second. So this is a volume per second, times n, which is the number of particles per unit volume. So that gives me the number of particles per second times the charge per particle. This is the charge per second. That's the current flowing. So I can substitute that for I. We introduced last time in a little bit more rigor that the current is NQAVD. So we'll make that substitution, and when we do, we get this expression here, which we call the Biot-Savart Law. So this looks kind of intimidating, right? It's an expression to calculate the magnetic field, but because it's a differential expression, we're going to have to integrate this. We're going to integrate it across the entire length of wire. So dl is the differential element. So you integrate over your differential element. That means we're going to integrate over an entire wire. Along the wire, each point is going to have a different direction from that point to the place where I'm trying to calculate the magnetic field. So r is going to change at different points. That means the r in the denominator and this r hat in the numerator will change. The current will be the same, and I'll integrate over the entire wire. So it's tricky because I've got to do an integral, right? So that makes it a little complicated. And I've also got this cross product, which makes things a little complicated. We need to think about right-hand rule, dl cross r, what direction is that? But for certain geometries, it's pretty straightforward. And this will work for any geometry. It's not always easy to do the integral, but I want to show you some examples where we can just brute force use this to calculate the magnetic field at a point from an arbitrary wire. So to do that, I'm going to have you draw your own wires. So go ahead and scan this code on your phone. You can dismiss the splash screen. And there's a button that says draw a wire. When you hold it, you can move the phone around and draw a wire or even a circuit through space. And it will take a moment. Mine's taking more than a moment. There we go, to calculate the magnetic field. And if you drew a crazy wire, you'll get this crazy diagram. And we can see a right hand moving along the wire, showing us the sense of the magnetic field, which way it's rotating around the wire. So we can also see the little arrowheads on the yellow field lines that were drawn. You can reset that. I maybe made too crazy of a wire. It'll be easier if I make something that's a little straighter. So you have to kind of move around to see it, in 3 dimensions. But whatever direction you drew the wire is going to be the direction that the current is flowing, or that it assumes the current is flowing. And the right-hand rule then will tell you what direction the magnetic field lines are curling. Okay, so let's go through how the phone is calculating this, because I think it's worthwhile to see how you might implement the Biot-Savart law in real life. So as you draw, it draws a bunch of dots, right, that make your wire. So you probably saw it as a bunch of discrete dots. And basically, it's just every few milliseconds, it's recording the position of a point in front of your phone. And that position is recorded as a 3-dimensional vector, so it's x, y, and z coordinates. So we could call the first point, point 1, the second point, point 2, point 3, and so on. So we have some number of points. If we look at some arbitrary point, here is the 11th one, we can call its position vector r0. And at some point in space, we want to draw a magnetic field, or we're going to calculate the magnetic field. So we'll pick this point out here, and we'll call that position vector r. And so the distance from our current element to our point in space is little r, which is going to be this big R minus r naught. So that's some of the geometry there. And then in terms of getting the direction of the magnetic field at this point, we're going to use the Biot-Savart law over here. The direction is going to come from dl cross r. So dl is the direction current is flowing. And we can get that by basically going from the point just before the one we're evaluating to the point just after. And that's going to give us a vector that points to the right here. So that's dl. And r hat is just the direction of this green vector. And so dl cross r hat in this example, if you use your fingers from your right hand, point them along dl, orient your hand to curl them into r hat, your thumb will point into the page. So we get the direction here from that cross product, which is roughly into the page for this particular diagram. So here's the Biot-Savart law as written in the notes. There are two things that we can do to change it, to make it more useful. The first is r hat, the direction of this vector, can be described as the magnitude, or the vector itself divided by its magnitude. That would just give us r hat. So let's replace r hat with the vector itself divided by its magnitude. So when we divide it by its magnitude, we go from r squared to r cubed in the denominator. And now let's integrate this entire thing. So we'll integrate the whole thing, and then instead of getting the little bit of magnetic field from one little chunk of the wire, we'll get the total magnetic field from the entire wire. All right, and here's the code that does that. I thought I had it on a separate page. Okay, so here's the code that does that. The function b field takes some parameter r, which is just the position where I want to calculate the b field. And the very first thing I do is I describe the b field there as being 0. 0 in the x direction, 0 in the y direction, and 0 in the z direction. And then I do a loop over all the line segments. So il is the integer number of the line segment, the 1, 2, 3, 4, 5 numbers that I've got written up here. So for each line segment, the first thing I do is I find di, that's the direction of the line segment. That's determined by looking at the position of the one before it and the position of the one after it. And I find its position, which I call r naught. So these line segments are objects where these parameters are available. So for our purposes, I'm just getting the values that are shown up here in the diagram. And then little r, I calculate from the r that I was passed, the position in space, minus the position of my line segment. So I subtract those two things as vectors to get little r. And then I calculate the field components of the b field from that one particular line segment using the Biot-Savart law. So I've got this function Biot-Savart where I pass it the current as a vector, so it's got a direction, and r, this green vector. So here's the Biot-Savart law. It is, at its core, the cross product of I and r. So the cross product I, I'm defining as a vector pointing along dl, crossed with r. So I guess that's this over here. And then I'm multiplying that with the power of 1 over the magnitude of r cubed. So that's the 1 over r cubed that I have there. And that's it. I'm returning that as my field. I'm ignoring the mu naught over 4 pi because I don't care about the absolute scale of it for this particular demo. And so I return that, and I add that to my magnetic field that started as 0. And then I go on to the next element in the loop, and I calculate for the next point on this wire. And I go through every point in the wire, calculating the contribution to the magnetic field and adding it onto my value for b. And once I've gone through the entire wire, I return b. Okay, so some of these expressions that look very complicated and look like they would be hard to evaluate analytically, maybe, but they're still useful. because oftentimes the way we actually calculate things is not analytically, but it's using computers. And coding this in is relatively straightforward. It's just a few lines of code. Okay, so that said, for simple cases, we can actually evaluate some things analytically. So let's do a few example problems where we use the Biot-Savart law to calculate magnetic fields. Okay, so here is a current carrying wire. That's a very specific geometry. The wire comes in, goes around a quarter turn of a circle, and then goes out. And we want to calculate the magnetic field at point P. And we have current going through the wire. Presumably, this forms a closed circuit. I'm not shown the rest of the circuit, but if the wire goes far away and then comes back and forms a closed circuit like that, I can ignore the effect of this distant wire, because as it gets further and further away, it has less and less effect. So in essence, I'm just calculating the field from this part of the wire, but we recognize there must be a complete circuit in order to get current to flow. Okay, so I'm going to use the Biot-Savart law. So let me just write that out to start with. dB is mu over 4 pi times I dl cross r hat divided by r squared. And I'm evaluating at point P down here. So I'm going to break this into 3 parts. Part 1 is this straight wire. Part 2 is going to be the curved part of the wire. And part 3 will be the straight wire where the current goes out. So for part 1, our current is pointing down. And for a particular point on this wire, the distance to point P, I could calculate, and its direction is down. So this cross product is the cross product of 2 downwards vectors. What do you get when you cross 2 vectors that are parallel? You get 0. Okay, so what that tells me is I'm not going to have any contribution to the magnetic field from the straight part of the wire. And I can make the same argument over here, that my current is pointing out, my r hat is pointing in. When you have anti-parallel vectors, the cross product is 0 as well, because you have vector 1 times vector 2 times the sine of the angle between them. So for 0 or 180 degree sine, we get no contribution. So only the curved part contributes. So let me evaluate the magnetic field from the curved part. I'm going to say the magnetic field is the integral of all the little pieces of the magnetic field. So I can write that as mu over 4 pi, and now times I, and I will integrate this dl cross r hat over r squared. This stuff right here is a constant, so I pulled it outside of the integral. And what I have to do is pick a little chunk of wire right here to be my dl. Okay, now dl is a vector. It has a direction in the direction of current. So I know that's going to be sort of down and to the left for that little representative chunk. Now, there's a couple of ways to go about this, but if I want to add up all the little chunks from a point here at the 12 o'clock position to a point here at the 9 o'clock position, a straightforward way to do that is to say the angle subtended goes from 0 to pi over 2. Okay, so let me define an angle, theta, relative to the vertical, and I'll call that theta. And if I do that, then the width of this chunk dl can be described in terms of the angular width. So d theta is the width of this, the width subtended, the angular width subtended by my little chunk. And the length of the chunk is r times d theta. This is just the arc length of an arc on a circle of radius r for an angle of d theta when measured in radians. So I'm using this expression. This comes from the arc length here divided by the radius gives us the angle. In this case, the angle is d theta subtended by that arc length. Right, so when you measure an angle in radians, we could say that dl over r equals the angle, oops, in this case the angle I'm calling d theta, when measured in radians. So I'm just expressing this in terms of dl equals r d theta. So I have a value that I can plug in for dl. My r hat vector is a vector that points from my current element to point P. So you'll notice that's always going to be perpendicular to my current element because the current's going around a circle. The r vector points radially inwards. And I can use the right-hand rule to say that cross product dl cross r is out of the page. Okay, so the direction of this is going to be out. So let me rewrite this expression. My constants don't change because they're constant. My dl has a magnitude of r d theta, so let me plug that in. My r hat has a magnitude of 1 because it's a unit vector. And this cross product gives me a direction that's out of the page. So I'll just denote that with a dot and a circle. And in the denominator, I have to put the distance from dl to point P. And in general, that could be changing as I go around the wire. But for all the points in this circle, or this quarter circle, they're all in equal distance capital R. So let me plug in capital R in the denominator. So one of those factors in the denominator will cancel with one of the r's in the numerator. And I evaluate this with respect to theta, because now d theta is my differential element. And I'm going to go from a point that's at the top, where theta is 0, to a point over here where theta is pi over 2. So my limits of integration are from 0 to pi over 2. So I'm just integrating a constant. Or I'm integrating to get a constant that will be pi over 2. And a little bit of cleanup. I can get rid of the pi's. And it looks like there's a 2 and a 4 in the denominator. So I could call that 8. Bella. The pi over 2 is radians for 90 degrees. So I'm integrating the angle. I'm starting at a point up here where the angle subtended is 0. And I'm adding up all the chunks of wire until I get to the one down at the 9 o'clock position that subtends an angle of pi over 2 from vertical. Eric? The direction of r hat comes from measuring the position where I'm calculating the field from my current element. So from dl, r hat points towards P. Let me draw that on the diagram. So r hat, it's a little crowded, but r hat points from dl to the point I'm evaluating. That can be a little confusing because when we have a circular wire like this, it points inwards. And usually when we have circles, radial direction is outwards. But in this case, it's defined from the wire to the point you're evaluating, which in this case is inwards. And this cross product, dl cross r hat, dl cross r hat points out. Noah? This one or this one? The bottom R. So there's oh, I should still have the R. Thank you. Uh, I just missed that. There should still be an R there. Thanks. Okay, so we can check our direction. We said it was out of the page. We also said that a current carrying wire will have a magnetic field that circulates around it. And so we can pick a point here, point our thumb in the direction of the current, and the magnetic field circulates around and is pointing out at point P. And in fact, for every point along the wire, it's pointing out. So it makes sense that my final direction should be out. So I can get that two different ways. I can get it from the right-hand rule in the Biot-Savart Law, or I can get it from the right-hand rule of just thinking about magnetic fields circulating around wires in a sense given by the right-hand rule, where I curl my fingers. Vincent? This expression? Yeah. So just if you have an arc with arc length s on a circle of radius r, the angle subtended by that arc is s over r when expressed as a radian in radians. Okay? So I'm using that relationship here where I'm calling the arc length dl and I'm calling the angle subtended d theta. And so there's that relationship for the arc length rearranged to give me dl. Bella? Yes. It's always pointing towards the point where I'm evaluating the magnetic field. So I'm evaluating it, in this case, at this point here, P. So once I draw my little element of current, R hat points towards P. Vincent? To the what? So we're going to do some more of these. So seeing problems with different geometries should be helpful. Let's consider the magnetic field from a straight wire. And we'll consider a wire that has a finite length. It goes from plus A to minus A, which is kind of silly because you could never actually get current to flow through a segment of wire that doesn't complete a circuit. But it doesn't mean that we can't calculate the magnetic field that we would have from it if we did. And what we'll actually do is we'll calculate this first for a segment of wire, and then our result, which foreshadowing, here's our result, we'll take the limit as A goes to infinity, and that will give us a long wire. And again, long wires have circuits, but we often ignore the things that are far away. So if you're close to a wire, you can treat it as like an infinitely long wire. Okay, so the first step is to write down the Biot-Savart Law. So we have this expression here. It's complicated enough that you're probably going to have to look it up. I don't expect you to memorize this. But because it's a differential expression where we have this differential element of length L producing some differential magnetic field B, we need to sketch our wire and draw on our sketch some representative little element dl. When you're doing this is true for any sort of integration. You want to sketch like a representative element. Don't draw an element right at the center or at the very edge. Do it just at some sort of arbitrary position. Because if you try to do it like right in the center where there's some symmetry, there might be some, you might miss out on some of the parameters that are relevant. For example, the distance from this little element to some point P here along the central axis that bisects our wire, which is where we want to calculate the field. We want to calculate the field the distance r away from the center of the wire. Okay, so if we imagine this is the x-axis, a distance r away at point P here, the distance from our little chunk of wire up here, dl, to that point P is the hypotenuse of a triangle that I'll call r prime. I'm calling it r prime because r, I'm calling the distance from the center of the wire to my point over here. So if I'm at a height of z measured from the center of the wire, so the vertical axis is z, so I'm up here at a height of z, then this side is z, this side is r, and this hypotenuse is square root of r squared plus z squared. I'll also call this angle here between dl, which points upwards, and r, which points towards P. I'll call that angle phi, and I'm going to need that because when I take the cross product has the magnitude of dl times the magnitude of r hat times the sine of the angle between them. This is the angle between them. Okay, so I can substitute in for this expression the various relationships that I got, like r prime is going to be square root of r squared plus z squared. That's going to go into the denominator. I haven't quite done it yet. I do it in another step here. In the numerator, my dl, I'm going to call that dz times k hat. So it's a vector. It has a direction, and it's pointing upwards, which is in the z direction. So k hat is a unit vector that points in the z direction. Its length is a little differential element, and since it's along z, I'll call it dz. So I'm going to end up integrating along z from minus a to plus a, so my differential element has to be dz. Okay, so I'm going to substitute this in for dl. dz times k hat, and this cross product has a magnitude that's the magnitude of dl, okay, well that's just dz, times the magnitude of r prime hat, that's 1, because it's a unit vector, times the sine of the angle between them. So here's that sine of phi. And now in the denominator, I'm going to plug in r prime is square root of r squared plus z squared. It's just the length of this hypotenuse. Right, so I'll plug that in for the denominator. And I note that for different positions along the wire, that hypotenuse is going to have different lengths. So it has to remain inside the integral. The other thing that I'm going to do is write this sine of phi in terms of these various parameters. So let me go over here to my board. I need the sine of phi in my expression. Well, the sine of phi is the same as sine of pi minus phi. It's a trig relationship. And calculating the sine of pi minus phi is straightforward. It's just the opposite over the hypotenuse. So I can say that sine of phi equals sine of pi minus phi, which equals the opposite over the hypotenuse. So here's that expression written in the notes. I'm going to plug that in for sine of phi. That's why I have an r in the numerator. I have the square root of r squared plus z squared in the denominator for my sine phi. And I have two factors of square root of r squared plus z squared in the denominator from my r prime squared. So I end up with 3 factors of square root, meaning r squared plus z squared to the 3 halves in the denominator. My r is in the numerator, and all these other things, I, mu, 4 pi, those things all factor out. And finally, I need a unit vector for direction, because I took the magnitude of this cross product, but I haven't dealt with the direction yet. So I'll use the right-hand rule. dl cross r hat is into the page. Or if I like, I can point my thumb along the direction of current and curl my fingers, and they're curling into the page at that point as well. So both of those arguments tell me the field should be into the page. So I'm calling that theta hat, In cylindrical coordinates, where z is up and r is out, theta hat circles around counterclockwise when viewed from above. So that's just notation that means into the page for this particular point. Okay, so that shows up out here. So what I'm left with is some constants times an integral. So I just have to do this integral. This can be solved using trig sub. I'm not going to go through the whole substitution. You can actually just look up this form of integral in an integral table. I'm happy to do that here. And then when I evaluate this integral and plug in the limits, this is the expression that I end up getting. Okay, so I have this direction that's into the page, 4-point on the right. It depends on the length of the wire, because I've got this a in the numerator. It depends on how far away I am. So as r gets bigger, the field gets weaker. And it depends on the current. A stronger current produces a stronger magnetic field. So I said this is probably not a very realistic scenario. We don't have segments of wire carrying current. We have long wires potentially carrying current. If we want to consider what happens for an infinite wire, we can just take this expression we got and take the limit as a goes to infinity. Right? A was the length of the wire was 2a. It went from minus a to plus a. So if we take the limit as a goes to infinity, we have an a in the numerator, but we also have a square root of a squared in the denominator. Right? So as a gets large, this r in the denominator becomes irrelevant, and we have something that's like the square root of a squared. And so the ratio of a over the square root of a squared is just 1, which means all this stuff, the a over square root of r squared plus a squared, that just becomes 1. And what I'm left with, the 2 and the 4 cancel to give me 1/2. And I get this expression for the magnetic field for an infinitely long wire. Mu I over 2 pi r. The theta hat just tells me it's circulating around counterclockwise when viewed from the direction the current is flowing towards. Okay, so here's our picture for what that's going to look like. This result is going to be useful because we're going to learn about an easier way to calculate the magnetic field next time using symmetry properties. And one of the symmetry properties will map nicely onto an infinitely long wire. So we should get the same result. So having derived this using the Biot-Savart Law, we're going to be able to go back and compare it to what we get next week using Ampere's law. Okay, any questions about how we went through this calculation? Bella? Okay. So r prime is the vector that points from my chunk of current, dl, to the point I'm evaluating the magnetic field at. So it's this vector, this blue vector that points all the way down. And the direction is derived from that, yeah. So r prime hat is that along that direction. Okay, how do I know it's theta? I wouldn't worry about the mathematical notation here. What I would worry about is, do you know that for this diagram it's into the page? So dl points up, r prime points down and to the right. So we have to have our thumb pointing into the page when we do that cross product. Okay, the reason we express it as theta, not into the page, is because we're getting an expression over here that's valid for any value of r. It doesn't care whether I'm evaluating out here or on the left side or behind this. And it's not always going to be into the page. If I come around, it's going to be out of the page over here or sideways over here. And that circulating direction we call theta in cylindrical coordinates. We'd have r being the distance away from the center, theta being the angle around, and z being the height. Okay, let's consider what happens when we have two wires. Let's consider two parallel wires carrying current in opposite directions here, I1 and I2. We know that a current carrying wire will produce a magnetic field. Okay, for I1, that magnetic field we get from the right-hand rule is going to circulate clockwise. And that means that current 2 is going to be moving in a magnetic field. We have moving charges in a magnetic field because wire 1 is producing a downwards magnetic field at that point. Likewise, wire 2 is producing a downwards magnetic field in the middle. But what that means is each of these wires is going to be carrying current in the presence of a magnetic field from the other wire. And when charges move in a magnetic field, they experience a force. Right? So charges moving in wire 2 are coming out of the page. Wire 1 is producing a downwards magnetic field there. QV cross B means this will experience an outwards force. Likewise, wire 1 is going to feel a magnetic field pointing up from wire 2. The charges are flowing into the page, so QV cross B, that's going to experience an inwards force. One of those two things is not correct. They can't both be exerting a force to the right. What did I do wrong? Wire 1 produces a downwards field at this point. Current is coming out. V cross B produces an outwards force. Newton's third law tells me wire 2 has to push outwards on wire 1. And we should be able to get that from the magnetic field from wire 2 is pointing up. I've got V cross B pointing to the right. Now I'm just confused. Let me skip over this. Okay. Let's work out numerically or algebraically the strength of the force between two parallel wires carrying a current. We know the magnetic field from a long straight wire is mu I over 2 pi r. We just calculated that. We also know the direction can be found from the right-hand rule, and will circulate around the direction of current. We also know the magnetic force on a wire is IL cross B. We went over that on Tuesday. And so now if we have our two wires, one of them will produce a magnetic field, the other will experience a force from that magnetic field. Okay, so for wire 1, the magnetic field should circulate like this. Point your thumb into the page. The magnetic field circulates around that in the direction given by the right-hand rule, which tells us the magnetic field over here from wire 1 is going to be pointing down. Now, the force on that wire is given by IL cross B. So our L vector, in the direction of the current, is out of the page. L cross B produces a force that's to the right. So this is the force on wire 2 from wire 1. Now, wire 2 is producing a magnetic field that, again, using the right-hand rule, if our thumb points out of the page, that's going to circulate around and point downwards. So the magnetic field from wire 2 points down. And now the force that wire 1 feels, again, we're going to use IL cross B. So our moving charges are moving into the page. That's the direction of L. Cross B points to the left. Okay, so now it's working. I don't know what I was messing up before, but I get that the force from wire 1 on wire 1 from wire 2 points to the left. So Newton's third law tells me that these forces have to be in opposite directions. So I can validate that by using my expressions for the force on a moving on charges in a current carrying wire. And what I see is that if the parallel wires are carrying current in opposite directions, they repel. So in this top case, these wires are going to repel each other. That means in the bottom case, they're going to attract. So if you have parallel wires, let's say electrical transmission line, where current flows along one wire and then back along the other, those wires are going to repel each other. You can actually see this in the wires from transmission lines. They're going to bow out slightly if they're carrying a large current. Okay, so the magnitude of the force we're going to work out. We know it's IL cross B, and we know the direction and the magnitude of the magnetic field. Magnitude is mu I over 2 pi r. And if the wires are parallel, then the magnetic fields are necessarily perpendicular to the current. Right? So we saw that in this case. The magnetic fields are pointing down, the current was out of the page. In fact, if I draw my currents going into and out of the page, the magnetic fields are in the page, so they're always going to be 90 degrees apart. So that means the magnitude of this cross product is just IL times B. The sine of the angle between them is 1. Right? They're 90 degrees apart. So the force on one of the two wires, when you have a pair of current carrying wires, is going to be ILB, where B is mu naught I over 2 pi r. So this I is the current in the wire you're calculating the force on. This is the magnetic field from the other wire. So this is the current in the other wire. When we put those things together, we get mu I L over 2 pi d. We're calling d the distance between the two wires. So this r becomes d. One of the currents is I1, the other current is I2, so that's why we have those two things. And I'm assuming that this is in free space, so we're going to use mu naught to represent the permittivity of free space. So what we see is the force between two wires depends on how long they are. Right? As you go further and further along, there's more wire pushing on each other. So what's useful is to express the force per unit length. So divide both sides by L. And we get this expression here. And the greater the force, the greater the currents in the wires, the greater the force between them. And the closer the wires, the greater the force. So if you have two wires carrying current in the same direction and you bring them close together, eventually they'll pull each other together and snap together because they're attracted. And as they get closer, the force gets greater, and that will eventually just pull them together. Other geometries where we want to be able to calculate the magnetic field, because we see these geometries a lot, are in a loop and a solenoid. A solenoid is just a bunch of loops. So let's start with a single loop and then generalize our result to a solenoid. Imagine we've got some current coming in, and then it goes around a circular path, and then it leaves. In such a way, I guess as drawn, it's going counterclockwise. We want to calculate the magnetic field at some point along the axis, and we'll say, let's calculate a distance x away from the center, so over here. So what we do is we pick a little chunk of the wire, and we'll call that chunk dl, and we write out the Biot-Savart law integrating over all of the wire. So we have mu over 4 pi I dl cross r hat over r squared, and we're going to integrate to get the total magnetic field. So for this little chunk, it's the value of r in this expression goes from the chunk to the point I'm evaluating. So in this case, it's this blue arrow pointing down and to the right. This cross product, I can see dl and r are always going to be perpendicular. So the magnitude of this cross product is just the magnitude of dl. That's it, just the magnitude of dl. The magnitude of dr hat is 1. The sine of the angle between them is 1. So it's just going to be dl. This r hat, or this distance from my current element to my point, is going to be a constant. For any point around the loop, it's going to be the square root of x squared plus a squared. So I have this value for r. And the last thing that I want to do is consider that as I move around, the direction of the magnetic field that I'm producing, so dl cross r is a direction that I get from the right-hand rule. It's sort of pointing up and to the right here for this particular little chunk of wire. But a point on the bottom would have dl going in the opposite direction. It would produce a magnetic field that's down and to the right. So by the time that I integrate all of the little chunks around this loop, all of the vertical components of the magnetic fields will cancel out. So it's only the horizontal or the x components that are going to add up. So I only need to figure out what the x component is. And the x component of the magnetic field is going to be the magnetic field from my little chunk times the cosine of theta. Well, the cosine of theta, this theta right here, is the same as this theta right there, right? Because, let me switch over to my drawing. If this little chunk is theta and this is 90 degrees, then this has to be 90 minus theta. And because this is a right triangle, these angles all have to add up to 180, which means this angle has to be theta. Okay, so the cosine of theta, which I care about to get the x component of the magnetic field, I'll look at this angle over here. The cosine is just the adjacent over the hypotenuse. So it's a over square root of a squared plus x squared. So I'm going to plug all these things into this integral. And what's interesting is nothing changes in the integral. So all of these things are constants. They all come on the outside. The only thing that I'm integrating over is dl, this little element of length. And I'm going to go all the way around the perimeter of the loop. So from 0 to 2 pi a. And on the outside, I have my mu I over 4 pi. I have my a in the numerator that comes from this cosine. And I've got the a squared plus x squared to the 3 halves. So 2 halves come from this being squared, and the 1 half comes from this. Okay, so the integral here is trivial. I'm just integrating from 0 to 2 pi a, so I just get 2 pi a. And the 2 pi cancels this 4 pi and leaves me with a half. The a times that a gives me this a squared. And my direction, I argued, would be in the x direction, so I'm calling that I hat here. And here's my expression then for the magnetic field from a current carrying loop. And if I want to evaluate this at the center of the loop where x equals 0, it simplifies quite a bit. And I get mu I over 2a at the center of the loop. So that's useful because we're going to have lots of examples where we have circular loops of wire. In particular, electromagnets, solenoids, are made of many turns of a wire. So we can treat it as just, the reason you do that is to increase the magnetic field from a single turn to n turns. So if we let n be the number of loops in a tightly packed solenoid, we can imagine the magnetic field in the center is just n times that of a single loop. So in the core of a solenoid, we get this expression for the magnetic field. Okay, and again, we have something circulating around. The current is circulating around. The magnetic field is going to go through the center in a relatively straight line. And we can find the direction by the right-hand rule. When you have something that curls, curl your fingers in that direction. And that will leave your thumb pointing in the direction of the magnetic field, in this case in the center of the solenoid. Or for this diagram down here where the current is circulating around like so, we get the magnetic field going through the center, and this acts like an electromagnet where the north pole is on the left because the field goes through the center from right to left and comes out and goes back through the other path. Okay, so we'll stop there.